Good morning, 1311 students. Today we are going to finish your chapter 3, Stoichiometry of formulas and equations. We are going to focus on two major topics. The first one is related to the balancing, writing the chemical equations. Second topic will be focusing on the calculations of quantities of your reactant and products. Particularly, we are going to focus on the molar ratio for the balanced equation, reaction sequences, limiting reactants, and also the product yield. Related to the solution stoichiometry, we are going to learn more in the future chapters. Particularly, we are going to learn molarity, moles per liter. You use the number of moles divided by the total volume to derive to obtain the molarity. We are again going to study moles, mass, number of entities conversion, study preparation and dilution of a solution. Our first topic will be the chemical equations. A chemical equation uses the formulas to express the identities and quantities of your substances involved in the physical or chemical changes. For example, you have 1 mole of hydrogen gas reacted with 1 mole of fluorine gas. You are going to produce 4 moles of hydrogen fluoride. Based on what we learned by the law of mass conservation, you are going to see you have 2.01216 grams of hydrogen, 38 grams of fluorine, 40 grams of hydrogen fluoride will be produced. In this case, we are going to write down the chemical reactions. Hydrogen gas plus fluorine gas produce 2 moles of hydrogen fluoride gas. The formation of hydrogen fluoride gas on the macroscopic and molecular levels. And then in the chemical reactions, we need to know on your left-hand side, you have magnesium plus oxygen. These two on the left-hand side, you call them reactants. And then on your right-hand side, this is your products or product. And in between of your reactants and products, you use a yield arrow to represent it, pointing the reactants to the products. So the equation must be balanced, meaning the same number and types of each atom must occur in both of the reactants and product sides. In this particular reaction, your magnesium, you have 1 mole, your oxygen atom, you have 2 of them. So in your product, you have 1 mole oxygen. So in this case, the reaction is not balanced. Therefore, we need to balance your chemical reaction. How to do the balanced chemical reactions? Totally, we can have 4 different steps or 5 different steps. First of all, you are going to translate the statement into an equation. For example, your magnesium and the oxygen gas, they are going to be combined together, produce a white powder. So this is a statement. You are going to convert magnesium metal and oxygen gas which reacted to produce magnesium oxide. Convert this statement into a chemical reaction. Mg plus O2 to produce MgO. This chemical molecular formula needs to be written down accurately. If you don't know how to do it, make sure go back to your chapter 2 related to the nomenclature. And then you balance the atoms using coefficients. Formulas by itself cannot be changed. O2, that's the formula for your oxygen molecule. You don't change it. Therefore, you're adding the number in front of your elements or compounds to represent coefficients. Oxygen, you have 2 atoms. Product, you also need 2 atoms. Therefore, you multiply by number 2. for your magnesium oxide. Similarly, magnesium, you need 2 moles. If it's necessary, we need to adjust these coefficients. If you have a fraction, it's not a whole number, you need to convert the fractions into the whole number. And then you're going to double check the items whether they're balanced or not. You check all items balance. The last step, you are going to specify the states of the matter. Your magnesium, solid, oxygen, gas. Magnesium oxide is also a solid. That's the 5 different steps for us to balance a chemical equation. Sample problem. Our problem is, within the cylinders of your car engine, the hydrocarbon octane, which has a formula C8H18, octane C8H18. This octane is one of the many components of your gasoline. In the car engine, the gasoline octane mixes with your oxygen from the air and burned to form carbon dioxide and water vapor. Write a balanced equation for this chemical reaction, which is a combustion reaction. Our plan. You are going to translate the statement into a balanced reaction. And then you balance all the items by using coefficients. Followed by, if necessary, we are going to adjust the coefficients and then check the atom balance. The last step, specify the phases, the states of the matter. Our solution. Your octane C8H18 reacted with your oxygen O2, produces CO2 and H2O. You are going to determine the total number of atoms. For your carbon, you have 8 in reactants. You need 8 for your products. And then go to hydrogen. You have oxygen, hydrogen. Which one you are going to balance first? You balance the one which is simpler. For my hydrogen, I have 18 in the reactants. I have 2 in my products. Therefore, the H2O, water vapor, need to multiply by 9. And then count the total number of oxygen. For your reactants, you have 2 oxygen atoms, oxygen in your product, 8 times 2 plus 9 times 1, 25 in total. Therefore, so your oxygen in your reactant, 25 divided by 2. This coefficient, 25 half, is not a whole number. Therefore, we are going to adjust the coefficients by multiply by 2 for all of the reactants and the products. So your octane C8H18 multiplied by 2. 25 divided by 2 multiplied by 2, 25. Carbon dioxide, 8 times 2, 16. 9 times 2, 18 for your water. And then you are going to double check the atoms balancing. Carbon, I have 16. Carbon 16 for your reactants and products. Hydrogen 2 times 18, that's 36. 18 times 2, 36. Oxygen, I have 25 times 2, 50. Oxygen in your carbon dioxide is 32 plus 18 in water, 50. Therefore, the total atoms are all balanced. The last step, you are going to specify the phases. Octane, everybody knows gasoline is a liquid, and atmosphere oxygen is a gas. Carbon dioxide is a gas. Water vapor, vapor meaning gas. So this reaction, this equation is a balanced reaction with the labeling of the different phases for the reactants and the products. Afterwards, we are going to determine the stoichiometric calculations. The coefficients in a balanced chemical equation has very important significance. The coefficients represent the relative number of reactants and products. The coefficients also related to each number of moles for your reactant and products. The coefficients, they are related to the moles, not grams, not liters, but moles. The moles are related to the mass. Therefore, the equation can be used to calculate the mass of reactants and products for a given chemical reaction. So the molar ratio from the balanced equation are going to be used as the conversion factors. So how do you do this conversion? Again, mass to moles, moles to entities, moles to mass, moles to entities. What you can see, the number of moles of your reactant and the product are the bridging stone, are the bridge. So you are going to convert moles to moles from reactant to product, vice versa, and then from there you calculate the mass for reactant, calculate the entities for your reactant. Similarly, from moles you calculate the product mass called product yield, and also you can calculate the entities for your products. Again, your molar ratio between reactants and products are very important. Those molar ratios are reflected by the coefficients. For example, calculate the quantities of reactants and products from moles to moles. Our problem is copper is obtained from copper 1 sulfide by roasting it in the presence of oxygen gas to form powder carbon 1 oxide and gaseous of sulfur dioxide. The question is, how many moles of oxygen molecule are required to roast 10 moles of copper 1 sulfide? Our plan. First of all, you are going to write it down, the balanced reaction, and then you are going to use the molar ratio as the conversion factors from your reactants to products or vice versa. Solution. So you write it down, the balanced reaction. Copper 1 sulfide, which is a solid, reacted with your oxygen gas, produce copper 1 oxide, so Cu2O and sulfur dioxide. You balance this reaction. My balanced reaction is 2, 3, 2, 2. And then you are going to convert 10 moles of copper 1 sulfide, Cu2S, multiplied by the molar ratio between oxygen and the copper 2 sulfide. From your balanced reaction, your copper 2 sulfide, 2 moles, produce 3 moles of oxygen dioxide, requires 3 moles of oxygen molecule. Therefore, you use 10 times 3 divided by 2. The answer is 15 moles of oxygen molecule are required to roast 10 moles of copper 1 sulfide. Sample problem question 2. Calculating the quantities of reactants and products based on the moles to mass ratio. Still, following by the above question, you are going to roasting your copper 1 sulfide. The question is how many grams of sulfur dioxide form when 10 moles of copper sulfide reacts. Our plan, using the balanced reaction, the same as the previous one, to gain the moles of copper 1 sulfide, which is 10 moles, and using the molar ratio as your conversion factor to determine the moles of sulfur dioxide, SO2, and then you calculate the molar mass of sulfur dioxide, multiply the moles by the molar mass to determine the mass in grams of sulfur dioxide. The mass must be in grams. Solution, balance the chemical reaction. Again, 2 moles of copper 1 sulfide, 2 moles of Cu2S solid, plus 3 moles of O2 in gas phase, produce 2 moles of Cu2O solid, plus 2 moles of SO2 sulfur dioxide in gas. And then 10 moles of copper 1 sulfide, 10 moles converted to moles of sulfur dioxide. From your balanced reaction is 2 to 2. So therefore, 2 moles of sulfur dioxide requires 2 moles of copper 1 sulfide. You determine the moles of sulfur dioxide and then calculate the molar mass of sulfur dioxide. Sulfur is 32.07, oxygen 16.00, two of them. So 32.07 plus 16.00 times 2 gives you 64.07 grams of sulfur dioxide in per mole of sulfur dioxide. The total mass of sulfur dioxide will be 641 grams. I believe I do have one more question, which is calculate the moles, calculate the quantities of reactant products from mass to mass. Again, above question, so you are going to roast. You are going to actually produce 2.86 grams of copper 1 oxide. I want to know how many grams of oxygen is required. Again, our plan, write down the balanced reaction, convert the mass to moles, and then using the molar ratio as the conversion factor, determine the moles of copper sulfide, copper oxide, and then multiply by its molar mass to determine the grams. The solution, again, you write down your balanced reaction. In your question, you convert 2.86 grams of copper 1 oxide, Cu2O, convert these kilograms to grams. 1 kilogram equals to 1,000 kilograms. And then you divide it by its molar mass of copper 2 sulfide, copper 1 sulfide, Cu2O. That molar mass is 143.110 grams per mole. And then you determine the moles of your Cu2O. Based on the moles of Cu2O, you calculate the moles of oxygen. Again, Cu2O, 2 moles, equivalent to 3 moles of oxygen molecule. And then you multiply by the molar mass of oxygen, which is 32.00 grams per mole. You determine the grams, and then you convert grams to kilograms. 1 kilogram equals to 1,000 grams, or 10 to the power 3. Therefore, you can determine the kilograms of oxygen. Again, the moles are the key point. You convert kilograms to grams, convert grams to moles, and from the molar ratio between the reactants and the products, oxygen and copper 1 oxide, so you can convert the moles of oxygen or copper oxide to oxygen. From there, you calculate the grams and then convert grams to kilograms. Followed by the limiting reactant. So far, we have assumed the reactants are present in the correct amount to react completely. This completely reacted reactant is called limiting reactant. Your limiting reactant will be completely consumed up in the reaction first. In the reality, only one reactant will limit the amount of the reactants, of the amount of the product or products that can form. The reactant which limits the amount of product is called limiting reactant. The reactant which is not limiting will be in excess. Some of the reactant will have the leftover. So I give you an ice cream analog for you to understand the limiting reactant. For example, in order to produce a sundae ice cream, you need 2 scoops of ice cream, 1 cherry, 50 milliliters of syrup. What you have 8 scoops of your ice cream, 6 cherry, 100 milliliters of syrup. In this case, B, which one is your limiting reactant? I heard syrup, yes, syrup. So how many sundae you are going to make? 2. Yes, your product will be 2. This ice cream will be completely consumed up first. And then you use the amount of this syrup, the limiting reactant, to calculate the product yield. And after the reaction, this syrup has nothing left. But your ice cream and the cherry, they do have the leftover. The one which are not limiting reactant will be in excess. Let's try a calculation. Sample problem. Calculating the quantities in limiting reactant problem. Moles to moles. Problem. In a preparation of ClF3 chlorine trifluoride, you use 0.75 moles of chlorine to react with 3 moles of fluorine. I want to know what is the limiting reactant. Possibly you can calculate what's the product yield. Plan. In order to find the limiting reactant, we are going to calculate the moles of your product, which can be formed from each reactant, chlorine and fluorine. And also we must write it down the balanced reaction accurately. And then you can use this information to construct your reaction table. Solution. Step 1. Balance the chemical reaction. Chlorine gas reacted with fluorine gas to produce chlorine trifluoride gas. So you have 2 moles of chlorine atom. Therefore, chlorine trifluoride you need to multiply by number 2. And then totally you have 6 moles of fluorine atoms. So you need to multiply by 3 for your fluorine molecule. And then you are going to calculate the product yield for your chlorine trifluoride from chlorine and fluorine. The first one, let's try fluorine. You have 0.75 moles of chlorine. Based on your chemical reaction, 1 mole chlorine produces 2 moles of chlorine trifluoride. So your product yield should be 1.5 moles. Similarly, let's use moles of fluorine. 3 moles of fluorine. Based on your chemical balanced reaction, 3 moles of fluorine will produce 2 moles of chlorine trifluoride. So the product yield for chlorine trifluoride will be 2.0 moles, which means your chlorine will be consumed up first. The one give you the least yield, the less yield. That reactant is your limiting reactant. So in other words, your chlorine Cl2 is the limiting reactant because it produces less product yield. Up to this point, we essentially finished what we did for this class, but you do have something we call the theoretical yield, like we just discussed, 1.50 moles, that's your theoretical yield. And then you want to calculate the mass, so you are going to measure the actual total amount of the yield. So you use your actual yield divided by theoretical yield, gives you the yield percentage. So this is again will be practiced in your ALEX homework. And then about the solution stoichiometry, what you need to know is about many reactions will occur in the aqueous solution particularly. Solution consists of 1 or more solutes which going to be dissolved in a solvent, meaning solution is a mixture. You compose at least 1 solute and 1 solvent. The concentration of a solution is given by the quantity of your solute present in the solution with a given amount of quantity, such as 2 liters, 500 milliliters. And then your molarity, capital M, italic capital M, is often used to express the molar concentration of the solution. Molar concentration equals to the moles of your solute divided by the liters of your solution. Moles of your solute divided by liters of solution. Otherwise, you have to do the conversion from other unit to the liters. And then you are going to also learn about the dilution of a solution. C1 V1 equals C2 V2. At this point, we finished our lecture number 3 about stoichiometry, particularly related to the balancing reaction, limiting reactant, and product yield.